Mate, always experiments, 100%. I learned my trade through being an application scientist from the technical side, but then understanding the business side of the industry, that very much came from being a product guy. I'm an X-ray guy for life, so metrology. With the rate of change in this industry, if it's a new technology development roadmap, the accuracy runs out pretty quickly. He said, your product absolutely cannot work. The science is broken. There's just no way. I would say in general, manufacturability first, because it's a high bar, right? Can you deliver the task assigned to you at the right price point? Horticulture, hands down. I grow flowers for a living. I think for young engineers, I would say podcasts, because it's that long format conversation with your peers that you just don't often get in our trade. And so we had this enormous challenge where not only do we have to look into new chemical systems, but then, when you got something that is so fragile and so easy to move, how do you deliver a chemical to that surface to then clean it? It's forecast that in 2040, the energy lost in interconnects will be equal to the energy usage of humanity in 2018. We've got rid of all those and just a single step batch immersion process. Mate, it's brutal, honestly. Like every town in Germany and Japan, I swear, has a wet process company. And he basically told me to sit down and watch an X-ray tool align itself 10,000 times. I was like, why?
Today, we speak with Oliver Whear, Director of Semiconductor Technology at RENA Technologies GmbH, a distinguished leader with a remarkable career spanning over a decade in the semiconductor sector.
With experience as a former product manager at Bruker and Ekstron, Oliver brings extensive expertise in compound semiconductors, 2D materials, and product management. His role at RENA Technologies involves developing the business by working with the community, customers, and academics to create product roadmaps based on technical challenges.
Prepare for an insightful discussion on translating industry roadmaps into concrete equipment specifications and advancing wet process solutions. Let's dive in.
Hello and welcome back to the Semiconductor Leadership Podcast. I'm your host, Salah Nasri. And whether you are a industry veteran or someone that's just curious about semiconductor manufacturing, this is your podcast. I have a sincere favor to ask you all. We just hit 3,000 subscribers on YouTube, 10,000 subscribers on Spotify. But when I look at the back end with my team, we have more than 150,000 views, which means a fraction is actually following the show. So please kindly do me this just one favor. Click that subscribe button, because the more subscribers we get, the more powerful and influential we'll become to emphasize how important the semiconductor industry is to the world. So without further ado, ladies and gentlemen, I hereby would like to introduce our guest today. Oliver Whear is a 11-year industry veteran working at several points in FEOL, manufacturing on metrology, deposition, and wet process tools. He started as an application scientist before moving into product management, and his current role as Director of Semiconductor Technology at RENA Technologies. Oliver is an expert at developing new manufacturing technologies based on challenges foreseen by industrial roadmaps and market strategy. He has a Master of Science by Research in Physics from the University of York. He's a committee member at the Semiconductor Standards of EPL 47, member of the Compound Semiconductor Materials Work Group. He was former product manager at Ekstron in MOCVD solutions for 2D materials, and also was former product manager at Bruker for HRXRD solutions of compound semiconductors. So, ladies and gentlemen, Oliver, welcome to the show.
Having me. Much appreciated.
Great to have you here. Oliver, just before we start the show, I'd like to have some rapid fire questions with you, especially for those out there who don't know who you are. So it's best to start with these quick, rapid questions. So, physics at the University of York. Oliver, theory or experiments? Which one was more fun?
Mate, always experiments, 100%.
application scientist or product manager? Which role taught you the most?
Hard to say because they taught me very different things. So I learned my trade through being an application scientist on the technical side, but then understanding the business side of the industry, that very much came from being a product guy.
But FEOL, BEOL, where's the real magic?
That's like asking what's your favorite, like house in Harry Potter, isn't it? Front and aligned all the way.
All right. Deposition, metrology, or work process. Pick your favorite tool of trade.
I'm an X-ray guy for life, so metrology.
Yeah, defect and inspections, eh? Graphene or boron nitride, which has the brighter future?
I think that's a trick question. I would say it would be the TMDs, the 2D semiconductor layers, forecasting logic applications.
Cool. First thing that comes to your mind when you hear the word roadmap?
A little bit painful, right? It's well, roadmaps are interesting. So I would say they're a very, very valuable tool, but with the rate of change in this industry, if it's a new technology development roadmap, the accuracy runs out pretty quickly. But for equipment roadmaps, a bit more of a different story because you're obviously reporting to the manufacturing space. So you need that long-term stability so that you can plan operations.
Standard committees, exciting or exhausting?
They serve their purpose. So, the compound semiconductor work group, for example, really, really practical work for today's manufacturing community. And the EPL 47, really good work for the emerging materials community.
Fair. One word to describe compound semiconductors.
Amazing.
Logic or memory, which is harder to innovate on?
I think, from the perspective of the people doing it, they would both say it's extremely hard. So
both of them.
Depends.
Everything is hard. Logic or memory? Actually, we asked that question. Biggest misconception about 2D materials?
I think it's the ease of which they will scale.
Okay.
So, we have seen clear demonstration of these films being created at 300 millimeter, but to translate that into 1 million wafer starts a month, very different ball game.
Okay. The toughest customer question you've ever had to answer?
One time I had this customer when I was at Abrooker, and he really into this theory of X-rays, right? And he says to me, it wasn't really a question, it was a challenge. He said, your product absolutely cannot work. The science is broken. There's just no way. And I said to him, I was like, that's been in production for quite a long time, mate. Here's the equations. We didn't come to an accord that day. But
did he end up buying the tool?
No.
Coffee, tea, or energy drink in the fab?
Nothing in the fab.
None of it. Clean room. Extron or Brooker, which role was the biggest stretch for you?
I would say the Extron role because although my title was product manager, I also was responsible for my own sales cycle as well. So I had to handle things like quotations, contract reviews, working with the project management team. It was really all encompassing. And I never expected it to be that role. But it was really beneficial because it showed me so much more about the business side of the commercial side of a semiconductor equipment company.
What's your proudest project so far?
I think it was coming up with the working methodology to qualify GaN silicon epi wafers using HRXRD. So I came up with basically the whole X-ray metrology flow. If it was for a 650 volt device or a 1.2 kilovolt device, and a lot of work went into that, and it was really nice to be able to sort of enable any customer to see so much from what their epi's doing.
What's more important, pushing physics or pushing manufacturability?
Depends who you're talking to at the customer site. I would say in general, manufacturability first, because it's a high bar, right? Can you deliver the task assigned to you at the right price point? That's really what it comes down to. When you push physics first, you tend to try and propose a more elegant solution, which is fantastic for technology development, but they don't always scale.
One industry trend that excites you the most?
I think it's the adoption of compound semiconductors into what are legacy silicon marketplaces. More materials just makes the place far more interesting.
If you weren't in semiconductors, what field would you work in?
Horticulture, hands down. I grow flowers for a living.
There you go. Agriculture. Book or podcast, what would you recommend to young engineers out there?
I think for young engineers, I would say podcasts, because it's that long format conversation with your peers that you just don't often get in our trade. Like if you think about most places, you're employed to a factory and it's just you and your co-workers, right? And there's a few exceptions like Suwon or Cambridge or wherever, where you might run into someone in the pub and you can talk shop, but that's unusual. So if you're trying to get into the field, podcast is the way to go, I'd say.
What's your one-line pitch for RENA Technologies?
Our one-line pitch is we're trying to solve the challenges that everyone wants to but doesn't have the time to, making it cheap and easy.
Yeah.
That's our jam.
Give me the hard work, basically.
Yeah, exactly.
and I'll do it for you. Awesome. Thank you for that rapid fire round. I want to talk now about your career journey. And we go back from the application scientist to where you are today as Director of Semiconductor Technology. What milestones, be it at Bruker, when you're dealing with HR, XRD solutions, or Extron MOCVD for 2D materials, or FEOL roles as well, which one most shaped your perspective on semiconductor manufacturing?
So initially, it was very much the Bruker role because I got to see quite a large number of fab steps, albeit early in the front end of line. So I kind of covered everything from crystal growth through to epi. And then there was some really interesting work we were doing on FinFETs later on, and also some stuff with 3D NAND. But increasingly, I've actually found the wet process to be really key in my understanding of the manufacturing flow because it's so, ubiquitous in the fab. So there's, 25-30% of front end line steps tend to be a wet process step.
Sure.
So you suddenly get this view into every part of the flow, and if you couple that with a working methodology of trying to figure out where the wafers are coming from and where they're going, it really unlocks knowledge, which is very useful.
And if we look at your academic foundations, how would you say your Master of Science or Bachelor's by Research, of course, in physics at York University influenced the way you approach process development and metrology in production environments?
So the group I was attached to, there were two professors who ran it. One was Kevin O'Grady in the physics department, and the other was Atsufumi Hirohata in electronics. And the group was essentially a Seagate house. We're very strongly funded by industry, and Kevin, as a tutor in particular, was old school, hardcore teacher, and so he beat into us good industrial practices. Really on it with lab bookkeeping, making sure the designs of experiments were sound, having theory to back it up, and modeling it. And so what that did is, at the earliest point I imagine it could have in my career, it forced me into a working style, which was part of what the industry is today.
Looking at now in your role mandate at RENA Technologies, in terms of your scope of responsibility, as Director of Semiconductor Technology, where do you focus? Is it in the wet process architecture? Is it the selective cleans? Is it single wafer versus batch strategies or tool roadmaps?
So my role at RENA is to essentially develop the business for the products that we have. And what I do is I go out into the community and try and figure out what are the problems that need to be worked on in wet process, as many of them are kind of mature and don't necessarily need too much investment, or albeit maybe it's not worth the financial investment. And so what I'll do is I'll look very much on an application by application basis of Can we do something with a batch process, maybe with a chemical change or a process tune? Does this require single wafer innovation, like with our silicon carbide etching? That was a whole new architecture required to do, the first ever strain relief etch of silicon carbide with a wet process. So it's varied. But what it comes down to is essentially working with the fields, our customer base and the academics, to create a roadmap that's based on technical challenges that can be translated into our core platforms.
And when you look at from roadmap to tooling, I mean, of course, you're known in terms of your career dealing with technologies around foreseen challenges, right? So how do you translate industry roadmaps and market signals into concrete equipment specs and process modules at RENA?
It's an iterative process, and it's very much a team process. So there's people within the group who will focus on defining hardware requirements. So what are the handling capabilities that have to be? What are the mini environments? What kind of fab automation requirements are there? And then within my team, we worry about what's happening at the nanoscale. And so it's a lot of work. Often companies will have several product managers collaborating to build specifications. What you'll do is you'll first define a market requirement specification, which is, as it sounds, based on an average of who we've spoken to, what do we think a minimum viable product is? And then you translate that into a product requirement specification, typically, which is kind of the data sheet that engineers need to then go and define the tool. And there will be all kinds of things in there, which are based around a concept, which is usually by that point already reviewed by a few key accounts who've bought into it.
And if you look at data and APC, I mean, what's your framework for tying tool sensors, SPC, and then you've got advanced process control to yield and excursion management in a variety of fabs that you're dealing with today?
Yeah. So with wet process, what the smart systems tend to come down to is control of the chemicals themselves, so the baths. So on board the tools, you're typically looking at things like concentration monitoring, enabling things like bleeding and feeding for minimum consumption of the chemicals. For some architectures like single wafer, you can have endpoint detection as well, which is a form of closed loop control. Or another thing is you can, this is quite easy to do. You can basically create a watch folder where a customer can input metrology data, and then you can use that metrology data to adjust recipes on the fly. So some people call it AI, but it's really closed loop control.
Close control, yeah. Or good software as well. I want to talk about, of course, the for the audience that may not be aware of how a line works, I think it's like 20 to 30% of a line is wet processing, right?
Yeah, that's right.
How do you ensure that RENA gets that position in comparison to the very highly competitive market that you're in already?
So it's a good question. When it comes to this, you have to break down kind of what are the typical applications, right? So about 80% of wet processes are cleans, and most of those cleans are standard cleans. It's literally called standard clean 1, standard clean 2, or an RCA clean. So the differentiator there really comes down to the cost of your product, the footprint, the automation grays, and to be honest, the relationship with the sales team and your ability to serve and support that customer. And that's true of some kind of more typical etches and strips, which make up the other 30%. But for RENA, which is within our semiconductor group, primarily a 200 millimeter focused organization, 200 millimeters where all the materials innovation is happening. And so, we are the only people working on, specific silicon carbide solutions, for example. We're also working very hard on gallium nitride, gallium oxide. And so we're trying to come to the customer and say, look, we are your R&D partner, and we're working on stuff on behalf of the community, and we can, enable that in your fab. On the 300 millimeter side of RENA, we're, the go-to place for prime wafer preparation. So, before it even arrives in the fab. So our know-how for particle control in a batch process is unmatched.
Marvelous. I want to go into, of course, the the deposition and 2D materials experience that you've had. So, from your Aixtron MOCVD work, and I know they focus on like the graphene and TMDs. What are the gating issues for 2D materials in CMOS lines, be it in uniformity or transfer or contamination, or even CMP or clean compatibility?
I think honestly, it comes down to clean compatibility. The reason is, fundamental to the materials. So 2D materials, they have what's called a van der Waals interface, which has got a very low mechanical strength. So, kind of if you push it, it wrinkles. Really, really fragile stuff. But often those interfaces are also hydrophilic. So if you have any water-based solution, it has a habit of sucking up and lifting off the 2D material. Problem is most cleans are water-based today. And so we had this enormous challenge where not only do we have to look into new chemical systems, but then, when you got something that is so fragile and so easy to move, how do you deliver a chemical to that surface to then clean it? It's a huge challenge.
If you look at integration pathways, which early product niches, be it in like sensing, if we say RF or BEOL, memory or interposers, look most realistic for 2D materials before they move into logic channels?
So I've been guided by a friend of mine. His name's Salim Akazi. He's the product manager for 2D at Aixtron today. And he really showed me this. So what he was working on, or is working on, I should say, is using 2D materials as a barrier layer for interconnects to essentially improve their efficiency or decrease energy loss. And so I really hope he doesn't mind me giving away his numbers, but he always brings up this figure, right? It's like, okay, if you look at the growing trend in microelectronics, it's forecast that in 2040, the energy lost in interconnects will be equal to the energy usage of humanity in 2018. So it's no joke.
Wow.
That is so much energy. So, I think, that's a great place to start, because my understanding is that the material requirements are less than, say, for a replacement of a gate-all-around structure.
Remarkable. I now want to talk about compound semiconductors. With wet work process and metrology needs for GaN and silicon carbide, even one might say even photonics differ from silicon logic, right? What changes in chemistries or tool materials and contamination controls are essential from your perspective?
So the working environments are very different. If you look at the cleanliness spec for a power device fab compared to a logic line, it's just a different ball game. It's like, I'm trying to think of an example. It's like trying to compare like an F1 car to an SUV, right? Both top of their game in the modern era, but just different. And so when it's coming into the compound semiconductor space, most typically, the front of the line guys are using kind of legacy silicon processes that have been optimized to just work in a manufacturing flow. But it's like I said earlier, once you start adding more materials, you have new challenges and new opportunities to innovate. And so this is where things get really interesting. So, for example, the fact that silicon carbide couldn't be etched until RENA with a wet process until RENA proved it, that was an example of innovation. Now we're working on some really interesting stuff in gallium nitride, micro LEDs and power devices, which are focused on the material to increase yields and decrease operational costs.
Intriguing. And, of course, one of the key things that kind of keep things fair, as one would say, would be the emphasis on standards and ecosystems. You're part of the work groups and you're part of EPL 47. How do your standard roles shape practical specs for cleanliness or materials compatibility and test methods? And what I would be interesting to know is, where are new standards most urgent today?
So standards are most urgent in emerging technologies. And believe it or not, even stuff that's being pushed out at some reasonable volume still isn't necessarily standardized. That's where the compound semiconductor work group is really valuable, So recently we've been working really hard on defining cleanliness standards for silicon carbide in terms of making sure there's a common understanding of the metrology and the definitions. That means then the community can speak apples to apples. And so, yeah, that work group is really practical manufacturing standards so that we can all, collaborate. And then the EPL stuff, that's run by the British Standards Institute. So it's very much a UK-led task on behalf of the nation. And there, it's much broader in scope because we can get anything from the material science fundamentally through, and it's more typical to the actual devices. And what I see there is a more R&D based kind of line of work today with some input into manufacturing. And I think the reason is it tends to be a lot of academics in that group, whereas Semi is the manufacturing guys internationally. So you just have, different individual experiences just shaping those committees.
And if you look at customer co-development, can you share a non-confidential example where collaboration with a device maker or material supplier led to a pivotal process or tool feature?
Yeah, absolutely. So a shout out to the silicon carbide community on this, right? So many people said to me, like, cleaning these wafers after CMP, it just sucks. And that kind of led me to a point of, why don't we just clean them? I'd only just started in wet process. I didn't know how hard this is going to be. But, the community defined the problem statement and they let us rise to the challenge, and they provided wafers, they provided metrology, they provided feedback. So it wasn't one particular customer. Everyone, helped us out. And then what that's allowed us to do is take us a cleaning process, which is typically multiple steps, like typically a scrubber, mechanical scrubber, maybe what's called a degreasing step with the spray tool, maybe then an immersion tool, and then in some cases even a single wafer final clean. We've got rid of all those and just a single step batch immersion process from CMP to EPI. So massive CapEx and OpEx reduction with the way we've managed to innovate.
And I think, if we talk about sustainability and cost of ownership, I'd be intrigued to know as well from a chemistry reduction and reclaim perspective, what are the most effective levers to reduce chemical consumption, wastewater and energy use in wet benches without sacrificing yield?
So it's really, it depends on the tool architecture, but in general, it's either reclaim or something like bleed and feed, where you're trying to keep a bath going as long as you can. Chemicals age, they change, they get used up eventually. And so at some point, you do need fresh chemicals. But what it comes down to is trying to optimize that process. And this is common in all wet process tools today, at the bleeding edge. So there'll be automated concentration monitors, there'll be smart systems for making sure the baths, at least this is true on the RENA tools, to keep those chemicals working for as long as we can. So a really great example is we have an etch bath called the silicon etch bath, which is for MEMS production. And if you run 500 wafer lots through our tool, we will only use about 100 liters of KOH, which is a 80% reduction based on the incumbent technology used before.
I see. And if you look at TCO and throughput, how do you balance cost of ownership? Let's say, for example, when you're at chemicals, you've got filters, spare parts as well, with throughput and defectivity targets. And what would be very vital to understand is which KPIs do you watch most closely?
So the KPIs that we watch most closely is meeting the minimum performance criteria of what we're trying to do. So if it's like, okay, you need to clean this wafer down to sub 20 particles, for example, that bit we have to do first, right? And then everything else, what we do is we match what is most important based on what does the customer feel is most important, right? So some accounts, they might only care, they might prioritize making sure the day shift engineers aren't too busy. So it's like, okay, what's our ease of use statement? Other people maybe are refurbishing an old foundry. Footprint is all, right? And that's why we have a number of different product offerings, basically to address what is the most important thing for whatever customer.
Intriguing. So if we look at like tool architecture and of course digitalization, especially when it comes to like single wafer versus batch, where do you draw the line between single wafer precision and batch economics? Because at the end of the day, especially for fragile features and tight CDU or LS bias budgets.
So we'll push batch until the last possible moment that an application allows us to do. For example, we patented a product of ours called the True Etch Tank, which is a batch etching system for metals and mesas, right? So we can get an on-wafer uniformity, about 2%, which, single wafer is 1% or less, right? So still a factor, 100% off, but is it good enough production? And for many of those use cases, of course it is. So, single wafer at the last minute for the most punishing applications, yeah, okay, fair enough. But until that point, we'll push batch for the low cost.
If we look at like software and traceability, which will be another key thing when you look at a fab, what role do recipe versioning? So, for example, you have like full lot, wafer genealogy, and then of course MES integration that has to come into play in accelerating the root cause analysis and continuous improvement.
Yeah, so in an ideal world, you'd be metrology rich, right? Well, obviously metrology is a cost, so I get it, right? Operations guys try to minimize it. It breaks my heart, honestly. But the more eyes in the fab, the better, because once you start seeing things drift out of target, there's only so many ways something can fail, right? Albeit there's a lot, but it is hopefully limited. So at least you can start to say, okay, if this is drifting out of spec in this place, likely chances are I need to do PM over here, right? So it's treating the cause before you have a real problem. And so smart systems, and I believe this is pretty normal, to be honest, these days, with the amount of data analysts out there, is looking at for specific KPIs, how are they changing over time, and at what point do you trigger what form of maintenance to fix it. But you're seeing this increasingly by the equipment vendors where they're doing onboard metrology. So epi reactors, right? They'll have in situ reflectometry where you can see warp, bow, thickness of your wafer and the epi stack respectively changing over time, and you can use that to tune the recipe as required. So it certainly is there today. How it can get bigger and smarter, I think really needs that high level view, which I certainly can't answer to, but I'd be very interested to hear what other experts would say.
Intriguing. What would you say? I mean, in terms of on a future outlook. So, if you look at the next 3 to 5 years, Oliver, which FEOL or wet process inflections are coming the fastest? I mean, could it be the EUV resist cleans? Could it be the backside power delivery cleans? Could it be selective deposition etch hybrids as well? Or I think maybe it might be a new solvent systems.
So solvent's an interesting one. For us at RENA, solvents are one of our key areas of expertise, because for whatever crazy reason, we don't seem to mind working with stuff that no one else wants to touch. So within our our own business cases, very large batch solutions of nasty solvents is a point of interest for us. But within the community, I think in the next 1 to 5 years, it's seeing wet processes that maybe unconsidered yet being adopted because the new material science of compound semiconductors allows them to be adopted. So some of the stuff we've got cooking for selective etching, for example, could be really interesting because it could enable new device types.
I see. It has to be mentioned, when you look at the industry, especially the wet processing world that you're in is full of competition. You have your APNSs, the SICONX, the screens, the TELs, the JSTs, and etc. How does RENA Technologies differentiate to all of these players?
Mate, it's brutal, honestly. Like every town in Germany and Japan, I swear, has a wet process company. and Pennsylvania, it's just like, it's nuts. Well, I'll be at a trade show and someone come up to me, it turns out they're a competitor and then the same size as us. And I'm like,
how?
What?
Why?
Where have you come from? And I think it's just because you just need a lot of wet process tools because there's so many wet processes. And they come in all shapes and sizes. You get the great big battleships for, hundreds of wafers an hour, all the way through to like little semi-auto benches for like single dips. And then there's just loads of dryers everywhere. So I think, when it comes to differentiation in the wet process marketplace is having a story to tell and being a good partner. So we found our good space by becoming a technology partner for the compound semiconductor community. It's like, I know I reference silicon carbide a lot, it's just because it's a handy case for us, but people said, you're the only people who are actually trying to innovate that material class. And it's true, we're right up there in GaN. We do a ton of work in indium phosphide as well, using some of our other patented technologies. So I think the fact that we're very much thinking as a solutions first company and looking at niche marketplaces. Well, niche from the perspective of maybe a 300 millimeter giant, but not niche to us, right? It's still big, still valuable. I think that's where we stand out.
Remarkable. I mean, what advice would you have to like other people in the industry that are just coming out from university? They might be going for the application scientist role, but if they're eyeing FEOL, I mean, what common pitfalls should they avoid, and where are the white spaces worth pursuing?
So there's a really good piece of advice I got from my first boss in the industry, a guy called John Waller Brooker, great mentor. And he basically told me to sit down and watch an X-ray tool align itself 10,000 times. I was like, why? He goes, because then you'll know. He was bloody right. Like, when you spend that much time sitting with your instruments, just working over and over again, you start to pick up on all the little details of what actually makes a machine function. And that literacy of understanding machines at their core, I think, is generally lost on the candidates that come into the workplace. So, most universities that we find aren't preparing scientists for good know-how of kit. An example that's different to this is Lewis University near Chicago. They make their students all build their own tool as part of their master's project, and you get the most amazing students because they understand how the sensors are working, what the software's doing, how all the encoder rails and stuff, how they all function, what that goes together is. So if you want to go into the industry, get your hands working on tools and spend time around them and get a feel for every little bit of it. And that will give you a much stronger technical foundation in the long term.
Marvelous. Oliver, this has been an absolutely remarkable discussion. I think I've learned a lot about the wet processing world that I wasn't aware of. We have a tradition on the show where the last person leaves a question for the next one. And the question that was left for you was, if there was another planet in the world apart from Earth, where would you consider living?
Oh, I'd quite fancy one of the moons of Jupiter, the one that's got that subsurface ocean. Yeah. Just for a cold dip.
For a cold dip, yeah. Or what's the thing that you lie down? Tubing.
Tubing.
Another one. Oliver, thank you for coming on the show. It's been an absolute pleasure. Sincerely appreciate it. To the audience, thank you for watching this Semiconductor Leadership Podcast. If you want to contact Oliver, you can contact him right here on his LinkedIn profile, or just pop up just here. And if you're interested more about RENA Technologies, the website is just below, and you can find out exactly all about them. If you enjoyed this podcast, again, like I said, please click that subscribe button and reshare it. Reshare it to people that if you found it valuable, pass it on to someone else that will find it valuable too. Because at the end of the day, as I always say, it takes a village to raise a chip. Other than that, take care, and I look forward to seeing you at the next episode. Bye for now.